structure, atomic structure of the atom. We have learned how the electrons are arranged in different orbitals of one atom. And we mentioned that among the electrons, we do have core electrons, which are very close to the nuclei. And we have strong binding with the nuclei. So we say that the core electrons are not active for making the chemical bond and express the chemical property. The second type of electrons is the valence electron, we will say. There are electrons in the outer shell of the atom, and we say that the electrons are active because they stand far from the nuclei, so they have weak binding energy with the nuclei. So they can be easily removed, where we start to discuss about the ionization energy. And we also mentioned about the electronegativity. So that means the capability of atom we receive electron. So you can now imagine that if one atom give out electron, then the other atoms should receive electron, because we have the famous law of conservation of the matter. So now in this lecture, we start to discuss how the atom using valence electron outside of the atom, in the outer cell of the atom, to create the chemical bond. Because we understand that in one molecule, you have a different atom, and the atom should be arranged in a specific manner. And the structure, the way the atom arranged will decide the stability of the molecule, the reactivity of the molecule. So before we look at the shape and the activity of the molecule, we may want to look at how each atom uses its electron, valence electron, to make chemical bond. Okay, so in this chapter, we discussed about the basic concept of chemical bonding. Here are the main content of this lecture. We talk first about the Lewis symbol and the Octet Rule. We talk about ionic bonding, covalent bonding, and we talk about the polarity of the bonding with the electronegativity of X atom. We will practice the drawing of Lewis structure, how we can use the dot to represent electron, and how we can arrange the atom, the electron, sorry, around the atom to express the structure. We talk about the resonance structure, and of course, in chemistry, when we talk about the rule, we will have exception of the rule. We talk about the octet rules, so we may want to look what could be the exception, though where the octet rule is not obeyed. And of course, we will discuss about the strength of the covalent bond. Okay. So when you look at different chemical bond, basically you can classify the chemical bond in three different families. First, ionic bonding. So you can find ionic bond in sodium chloride, potassium chloride in different sources. You can see in ionic bonding, you will have a cast ion, you will have a cast ion bonding with an anion through electrostatic interaction, we would say. The second family of the bonding is covalent bond. You can find the covalent bond in the molecule of water, CO2, oxygen, chlorides, and so on. Why I pick up specifically the case of water and CO2, because we are facing now a great challenge how to reduce the amount of CO2 in our atmosphere to keep the planet sustainable for the next generation. And the third family of chemical bond is actually the bonding between atoms inside metal. So inside the metallic crystal, the irons, aluminum, copper, how we can describe the bonding between the metal atom in this metallic structure. So in this class, we will focus mainly in the ionic bonding and covalent bonding. So for the case of metallic bonding, you may want to refer to the textbook, and maybe we will have some question later. So to recall, in the previous lecture, we learned about the periodicity of the element. So here is a general, most updated table of element. So you can see the concept of group of element. So group 1A, 2A, 3A, and so on. Group 3B, 4B, 5B, and so on. So on the group A, we call the main group, and the group B, we call the group of transition metal. And when you go from top to the bottom of the table, you have the concept of rows of elements. That means the element which have the same core electronic configuration. Okay, they will have the same core electron, but they have a different number of electron in valence cell. And of course, you may want to remember the evolution of the atomic radius, the size of the atom, when you move from the left side to the right side of periodic table of element, or when you go from the top to the bottom. You may want also remember the evolution of ionization energy when you move from left to right and top to the bottom of the periodic table of element. Okay. When we learn about electronic configuration, we learn how we can express, how we can write the electron configuration of one atom using the condensed structure. So in the condensed structure, you have the core electron present here equal to the electron of inert gas standing before the element you are considering. So here you have a core electron. So are very close to the nuclei, have a strong binding to the nuclei. So basically in the chemical reaction, they are not really involved in the making of chemical bond or breaking of chemical bond. So basically, in this chapter, we will focus for the moment on the core electron. And you have here the outer cell, we have valence electron. So you can see that all the chemical property go through the chemical bonds are involved, makes of the valence electron. So for the moment, we pay our attention in the valence electron. Again, I recall they stand far from the nuclei, so they have weaker interaction with nuclei compared with the core electron. So now, if you compare the sulfur and oxygen, you can see that basically the core electron will be different, but the valence electron are quite comparable. Of course, they stand in different layer. For the sulfur, the valence electrons stand in the layer with n equal to 3, and here you have valence electrons stand in the layer n equal to 2. So they stand in different distance with the nuclei, but basically they have quite comparable character. So that's why when you look at the valence electronic configuration of the two atoms, you understand that they have the same configuration S2B4. Okay, this can be different, like 2S2 or 3S2, but they have a similar S2B4. So that's why oxygen and sulfur, you can see here, oxygen and sulfur, they are in the same column because the valence electron is S2P4. So in total, you have 6 electron valence, and valence electrons stand in the orbital S and P. So that's why the atom, the oxygen and sulfur stand in the group of 6A. A, the main group, consists of all the elements where you have a valence electron localized in the orbital S and P. For the transition metal here, you have a valence electron involved S, P, and D electron. Okay, so that's something you may want to remember. Okay, back to the question of the valence electron in the sulfur and oxygen, they are quite comparable. Now, if you want to draw a chemical bonding between one atom A and B, like a bonding like A, B like this, you understand that the bonding will be involved, will be made of electron from the valence electron A and valence electron B. So the question, and practical question, is how can you draw the electron configuration of the atom A and the atom B so you can describe the bonding within the molecule AB when the two atoms bond each other. So how can you, and we understand that we use many the valence electron. So the question is how we can present one electron on the paper. So Lewis proposed a way to use a dot to present electron in a valence cell when we draw this electron configuration on a paper. Let's say if you take the sulfur, here you have 6 valence electrons, S and B. We will use 6 dots, 1, 2, 3, 4, 5, 6, to represent 6 electrons. And we understand that in one orbital, it can be occupied by a pair of electrons. So you can present 2 electrons like in a pair of electrons like this to represent the orbital which have 2 electrons. And if you draw here for B, so you have like this. So you say you have 1 pair of electrons, 2 pair of electrons, and 2 single electrons. So you have 1 pair of electron here, 1 pair of electron, and then 2 single electrons. So basically, the key take-home message is that Lewis proposed to use a dot represent 1 electron. So when you have a pair of electrons in one orbital, you can use a pair of dots. And when you have only 1 single electron in one orbital, you present by 1 single dot. Okay? So when you look at the Lewis symbol, using the Lewis symbol to draw the valence electron of the sulfur and oxygen, you can see that they are they are identical. Okay? Now, so take a look in the second row of element. You start from lithium, you have 1 electron, so 1 dot. When you move to the barium, you have 2 electrons, so you have 2 dots. Boron, you have 3. Carbon, you have 4. Nitrogen, you have 5. So you have 1 pair of electron and 3 single electron. Oxygen, you have 2 pair of electron and 2 single. Chloride, you have 3 pair of electron and 1 single. And for the neon, you have 4 pair of electrons. So here you have S2P6 with a total of 8 electron valence. Okay, so all the orbital have a pair of electrons. Now, when describing the chemical bonding, you need to consider a rules, which is octet rules. The octet represent 8. Okay, so the famous oct in the Greek language is 8. So you remember that when you learn in high school, you have a compound octan. Octan is compound have 8 electrons. 8 carbon. So octet rule is mean the rule consistent the 8 electrons. So atoms tend to gain or lose or share electron until they are surrounded by 8 valence electrons. Okay. So the rule is atom tend to gain, that means receive electron, lose, that means give out electron, or share electron with the other atom until they are surrounded by 8 valence electrons. Of course, you have some exception. For example, hydrogen, you have only 1 electron. So when you make the molecule hydrogen like this, then you can make the chemical bond with only 2 electrons. So hydrogen will not obey the octet rule. For the lithium, you have 3, and NO here, for example, the molecule NO, you have the nitrogen here, which will have 2, 4, 6, and 7 electrons, and it's not obey the octet rule. So now we may want to ask question, why octet rule? Why atoms tend to gain, lose, or share electron until they are surrounded by 8 valence electrons? So why 8 electrons? Anyone can comment? Anyone can explain? Hmm?
Can you repeat the question, teacher?
Okay. We are talking about the octet rules, right? And the rules states that atoms tend to gain, lose, or share electron until they are surrounded by 8 valence electrons. So my question is, why 8 electrons? Why is not 10 electrons? Why is not 9 electrons or 7 electrons, but 8 electrons?
May I?
Yes, please.
I think because the p subshell can contain maximum 6 electrons, and the s subshell can contain maximum 2 electrons. So I think so it can contain 8 electrons in the valence.
Yes, thank you. Exact. What do you say? So basically, we are talking about the main atom. So the atom in the main column. So you are talking about the atom. Which have S and P valence electron. So for S, you have a maximum at 2, and for P, you have a maximum P6. So in total, you will have equal to 8 maximum. Okay? So the octet rules is the most useful for the main group element, SP element. Okay? So here on the element, you can see the element of the main group in the on this table of element. For the element that I say which have electron in the orbital d, we talk about the transition metal. Okay, so all of the element will have a valence electron S, P, and D. So now, my question, you can observe, is that instead of obey 8 electrons, so octet rules, for the transition metal, because you have 1 orbital S, 3 AO B, and 5 orbital D. So in total, you will have 9 orbitals. So times 2 equal to 18 electrons. So it means that for the transition metal, instead of obey octet rule, they will obey the rule of 18 electrons. So that means the transition metal have a tendency to gain electron, to lose electron, to share electron until they have 18 valence electrons, which will be the stable state. Am I clear?
Yes, Professor.
Okay, good. Now, we go to the case of ionic bonding. So if you pick up the sodium metal here, so you have the electron configuration of neon 1s. Okay, so you have 3s, sorry. You have one valence electron, which is s1. And here you have valence electron, you have s2, b5, right? So you can see here representing by the Lewis structure. So you have 1 dot and 7 dots here. So the octet rule say the sodium will have a tendency to remove 1 electron to achieve the 8 valence electron. And the chloride will have a tendency to receive 1 electron. When you have 1 electron here, it's become like this. So you will have the octet rule satisfied. That means it have 8 valence electrons. So that's why when you put sodium and chloride, you will observe the tendency where the electron will transfer from sodium to chloride. So to make both sodium now become cation sodium, having 8 valence electrons, and chloride now become anion chloride, also have 8 electrons. So by that way, you have here 8 electrons and 8 electrons. So you make the molecule of sodium chloride, which perfectly inside sodium and chloride satisfy the octet rule. So in the same case for the potassium chloride, the octet rules can explain very well the ionic bonding when the atom tend to gain or lose electron until they are surrounded by 8 valence electrons. And I explained for the case of sodium chloride. So here, by applying the same rules, you can understand how mesenchymal oxide will be formed when 2 electrons from mesenchymal will send to the oxygen to make mesenchymal 2 plus, so cation, and oxygen 2 minus, the anion, satisfy octet rule. In the case of calcium chloride, because calcium can give 2 electrons, and chloride, X chloride can receive only 1 electron. So that explains why 1 calcium will bond with 2 chlorides, because calcium can give 2 electrons to obey the octet rule, but X chloride can receive only 1 electron to obey the octet rule. If it's 1 chloride receive 2 electrons, it becomes 9 electrons, so it will not obey the octet rule. So to make this happen, 1 calcium will interact with 2 chlorides. So for the same case of sodium sulfur, so sulfur needs to receive 2 electrons to become S2- with 8 electron valence cell, 8 valent electron, sorry. So, but 8 sodium can give only 1, so you need 2 sodium. So that's why you have Na2S. Okay. And they take sodium metal and put in the chlorides gas, and you will see it's a violent flame, and it's release a huge amount of energy. So we say that the formation of sodium chlorides from sodium and chlorides is exothermic process. Now, as we discussed about the formation of the ionic bonding, now we need to go a little bit more in detail. So why ionic bonding is formed? And we explain the metal ready to give up electron to make cation, the non-metal with high electron affinity. So that means it have high tendency to receive electron. So to receive electron transfer from the metal, so to make it anion. So now you have a cation, positive charge, and anion, negative charge. You have a strong interaction. So ionic bonding have some character, specific character. It's very hard. The camber with ionic bonding have high melting point. This is crystalline. The crystalline different compared with amorphous. Crystalline means the atom arranged in a well-ordered structure and in the long range. Okay, and the ionic bonding can be break apart along smooth flat surface. It's something you can imagine, like here you have a structure, a crystal. Imagine that you have here a layer of sodium, and here you have a layer of chlorides. So you can imagine that if you put a force here, you can remove this layer. So it separates this crystal into 2 parts. Another very famous example of how the crystal can be break apart from the smooth and flat surface is come to the graphites. So the graphites on your benzo can be released layer by layer, but I will not take here because it's not the ionic bond. But here in this case, the crystal of sodium chloride, for example, you can imagine that you remove 1 layer like this because it is in the crystal with well-ordered structure. So if you apply very high force, you can remove it. Ionic bonding formation is exothermic, as I mentioned, due to the attraction between the positive charge and the negative charge. This is. Now, we talk about the concept of lattice energy. So lattice energy is energy required to completely separate 1 mole of a solid ionic compound into its gaseous ion. So here is the equation. So you have sodium chloride, which is solid, S representing for the solid, and you need to put energy to break this structure to make sodium isolate cation in the gas phase and chloride in the gas state. So the energy required to break 1 mole of sodium chloride, we call the lattice energy of sodium chloride. Okay, because the bonding between the cation sodium and anion chloride is exothermic. So when we want to break it, you need to put energy. So the lattice energy is always positive. If you want to imagine it a little bit easier, you can pick up the energy diagram like following. So here you have energy, which is potential. Okay. So if you pick up the sodium and chloride gas in the separate form, you have you have high energy like this. Okay. So when you make sodium chloride solid, so the process is downhill. That means you go from the higher potential to the lower potential. So this process is exothermic. And you see, when it interacts, it becomes generate a huge amount of energy. So now, if you have sodium chloride crystal and you want to pick up, you want to break it, so you go in the opposite direction. So it will be uphill process. So if you want to use uphill process, then you need to put input energy. Okay, so that's why this energy always have positive value. Am I clear in my explanation? Yes. Is it understandable?
Can you explain, please? I didn't quite catch the.
Huh? Okay.
I didn't quite understand. Can you re-explain?
Never mind. Let's say so here you have potential. Okay. So when you have sodium and chloride in the separate phase like this, it generates a sodium chloride crystal. Okay. The sodium cation and anion have higher potential energy compared with sodium chloride crystal. So when they react, the interaction between the positive charge and negative charge, it will generate the sodium chloride crystal, and this process will release energy. Okay? So we call the process is downhill process. That means when you go from the top of the hill down, so you release energy, you convert the potential energy to kinetic energy. If you take the bicycle, you stand from the uphill and you go down. So you see the velocity of your bicycle will be accelerated because you convert from the potential energy to the kinetic energy. You can imagine, right? So now, if you are in the down of the hill, if you want to go up, then you understand that you are at the lower potential, you go to the higher potential, so you need to have energy input. So that's why you need to work hard to bring your bicycle up here, right? So that means you give energy to bring your bicycle from the lower energy to the higher energy. So here the process is uphill process. So the energy is positive value. So that's why when you break from the sodium chloride solid to make sodium cation gas and chloride anion gas, the process is positive in energy because you need to put energy to break it, to break very strong bonding. Okay. When the sodium and chloride anion react to make sodium chloride, it will release energy because the process is downhill. But now when you have a sodium chloride, you want to break it to become sodium cation gas and chloride anion gas. The process is uphill, so you need to put energy to break the bond. So that's why the lattice energy all the time have positive value.
Okay.
Now it's easier to understand.
Yes,
okay?
yes. Thank you.
Okay. And how can you compare? How can you imagine what could be the order of magnitude of this lattice energy? So imagine that if you have 1 mole of sodium chloride, so it's 23 plus 35.5 equal to 8.5 grams per mole, right? If you want to break 60 grams of sodium chloride, you need this amount of energy. You need to put this amount of energy, right? Almost 800 kilojoules. Now, give you one example to imagine. If you want to boil 500 milliliters of water, okay, half a liter of water, you need 170 kilojoules. So that means with this amount, you can boil almost 4.5 times of this, almost, let's say 4 times. So it's almost 2 liters of water. You can boil with the same amount you need to put to break 60 grams of sodium chloride. You get what I mean?
Yes.
So if you want to break the bonding inside sodium chloride, 1 mole, that means 58.5 grams, you need to put a huge amount of energy equal to the amount of energy you require to boil 2 liters of water. That's a huge amount of energy. Be careful. At the same time, if you pick up 60 grams of sodium chloride, you put in water, you can dissolve it easily. You don't need to heat it. The steam can dissolve it. Does that mean you don't need to put huge amount of energy to break the bonding of sodium chloride in water? You get what I mean?
Yes.
Can you feel my demonstration? So my question is there any confusion here? In one side, you say that with 60 grams of sodium chloride, you need to put a huge amount of energy to break the bonding to make sodium positive charge and chloride negative equal to the amount of energy you need to boil 2 liters of water, a huge amount. A huge amount of electricity, you need to pay money. But at the same time, if you pick up 60 grams of water, 1 mole of 60 grams of sodium chloride, 1 mole of sodium chloride, you put in water. The dissolution, so that means the separation of sodium chloride solid become potassium cation and chloride anion will be extremely easy. You don't need to heat it. You don't need to pay a lot of energy to make it happen. So is there any confusion here? Do you understand my question?
Well, I think there is no confusion because when you directly break sodium chloride into ions by giving the energy, it's only one process, and that direct process will cost a lot of energy. But when you add it to the water to dissolve it into the ions, there will be many other processes that may produce energy or take the energy. So the total energy of the whole process will be reduced. I think so.
So, excellent. Thank you, Vũ. Now, we go a little bit more. What are the other process that will produce energy to compromise that to the energy you need to put inside to dissolve sodium chloride? What are the other process you are mentioned about?
Well, I think there are like the Soviet process. I think so. Cái năng lượng xung phát hóa ấy ạ.
Okay, so solventation.
Yes.
Okay, so yeah, basically, you guys, we are talking about two things totally different. So we cannot compare two things different and confuse them. The dissolution process, that means you have sodium chloride solid, you put in water, so you make sodium X time. So here is liquid plus minus H2O X time, and it's liquid. This process have delta E very small. Okay. So at the same time, the lactic energy is the energy you need to put to break sodium chloride. Solid crystal become sodium gas and chloride gas. You see that here liquid and here they are gas. They are not similar. So if you want to put, if you want to move from here to here, you can imagine following. So you take the same sodium chloride solid, you put water inside. So this is dissolution process. Okay, so you have different species of sodium compared with the definition of lactic energy. So from here, from the sodium gas to the sodium liquid in water, you can imagine that you put water here. So you have the process of sodium gas plus water provides sodium H2O, liquid. That's solventation process. Solventation process. And this represents energy that we release. So here if E1 and the second also water, you have E2. So you can imagine that the total energy you have here, you will have E here equal to, then there is lactic plus E1 plus E2. So the lactic process have a positive charge because that is the endothermic, and E2, E1 have negative value because it's exothermic. So at the end, the total value of energy reduced significantly compared with the amount of the lactic energy defined here. So this solution of sodium chloride have nothing to see with the lactic energy you need to put inside to break the sodium chloride crystal to make gas ion and anion. Okay. Be careful because some of you may in with my experience of previous year teaching, some of you guys have this kind of confusion. So I take a few minutes to explain clearly here to avoid all of the confusion can have. Okay. So how can we calculate the lactic energy? If we have two opposite charge particle, one negative, let's say like this. Oof. You have a particle, a positive charge, and you have a particle of negative charge with a distance d here, and the charge here have Q1 and here you have Q2. So the potential energy of this interaction will equal to kappa Q1, Q2 over D. So you can see that for a given arrangement of ion, the lattice energy will increase when the charge of the ion increase. When you increase Q1, Q2, the value of potential energy. So the lattice energy will increase. And when you reduce the D, then that means you reduce the distance of the two charges, the lattice energy increase. Okay. So how you can reduce the value of D? If you want to reduce D, then you can imagine you reduce the radius of the atom. Okay, because when you have one atom and another atom like this, so we have the distance. So if you reduce the size of the atom, the distance between the two atoms will reduce. So you can imagine by this equation, if you want to increase the lattice energy, you increase the charge from positive to 2 positive. If you want to increase the lattice energy, the second option is reduce the distance between the two charges. So reduce the bond length between the two atoms. Okay. It's quite easy to understand. So now let's have a look. So here I give you one question. That's something you can have in the final exam. Arrange the following ionic compound in order of increasing lattice energy: sodium fluoride, calcium iodide, and calcium oxide. Which one will have highest lattice energy and which one will have a lowest one? What will be the order increasing lattice energy of the three compounds? So here can be the question of the final exam. Put what could be the correct answer expressing the increasing of lattice energy of three compounds: sodium fluoride, calcium iodide, calcium oxide. Question, the answer A, B, or C will be correct. Please work on that. You will have 2 minutes. Which one?
I think the answer is B.
Cháu không sao ăn được mì này. Cháu không thích ăn mì này đâu.
Ăn xong họ ngon lắm bố ạ.
Quẹ.
Thử ăn đi, không thấy gì cả, hộp thịt thôi. Lâm ăn đi Lâm, thịt đấy. Ăn nó qua cái mì tôm nó được cái chất gì?
Cái này cũng được cái chất gì?
Cái này có thịt.
Thế kia mà cháu thịt.
Sorry, you guys. Sorry, you guys are in the class. If you are talking about the oh my God. You are a big boy, huh?
Sorry, everyone.
Ay, ay, ay. Okay, let's go back to the question. So, what could be the correct answer?
Is B right?
Okay, so the correct answer will be B. Okay, the reason is following. You see that the lattice energy equal to kappa Q1 Q2D. Okay, so when you have the sodium fluoride, so that means you have one positive charge and one negative charge. Cesium iodide, you have one positive and one negative. Calcium, you have two positive. Oxygen, two negative. So here, for the case of Q1, Q2, you can see that Q1, Q2 for calcium oxide is 4 times Q1, Q2 for the sodium fluoride and cesium iodide. So you can see very well that the calcium will have the highest lattice energy. That's 14. Now, for the case of this Q1, Q2 of sodium fluoride is almost similar to Q1, Q2 of cesium iodide. So now important is looking at the D. Okay. So you know that in the group 7A, so the fluorides will stand in the first position, and then at the end you have iodide. So that means the radius of iodide will be larger than the radius of fluorides. The same thing for the 1A, you will have sodium and cesium at the bottom, like this. So you can imagine also the radius for the cesium is much larger than the radius for the sodium. So here you can imagine that the distance, the D of the cesium iodide will be larger than the D, the distance of sodium fluoride. So that means the sodium fluoride will have higher lattice energy because the distance is shorter. Okay?
I have a question, Professor.
Yep, please.
So in the formula to calculate the lattice energy you gave us, yes, but so Q1 and Q2 are numeric or ionic bonding, ionic charge, right? So one of them must be negative.
No, we are talking about the absolute value.
Oh, okay.
Professor?
Yep.
I could see that when you talk about the lattice energy of calcium oxide, but what if the radius of these two of calcium and oxygen is too large that it makes the lattice energy smaller?
Yes, good question. But you see that the Q1 and Q2, the result Q1, Q2 for the calcium oxide is already 4 times higher than the Q1, Q2 of sodium fluoride, right? And you will not see any chemical bond which have 4 times longer than other bonding. You get what I mean?
Yes.
Yeah. So the bond distance will be different, but not in the range of 4 times difference. So you can expect that the Q1, Q2 for the calcium oxide already 4 times. So even the distance increase, but let's say 2 times, then it will not change the order. You get what I mean? And here is something very important. Let's say later when you learn inorganic chemistry, for those who study chemistry more, then there's always a question whether between the atom A and B, there is one chemical. You got what I mean? So the chemical bonding we are talking about is the imagination of the scientist to describing the chemical phenomena of chemical compound. The bonding we don't see. You got what I mean? The bonding is our imagination, our explanation. On the ionic bonding, covalent bonding we are talking today, please take a message home that the bonding we are talking about is our understanding about the chemical compound and our imagination to explain later their chemical property. We cannot touch in the chemical bonding. We cannot see the chemical bonding. So what we can see? We can see in our experimental observation, we can see only the distance between the two atoms. Let's say experimentally, we have an atom A and with atom B, we can do the measurement of the distance D. We cannot see the electron here. You get what I mean? So all what we say A plus, B minus, or share A one electron, B one electron here to make the bonding is our understanding to explain the chemical character of the bonding between A and B. What we can see from the experiment is distance from A and D, A and B, the distance. This one, angstrom, we can see, we can observe experimentally. Then, when you measure the distance A and B, we may ask question, or other one will ask you question, whether between A and B exists one chemical bond. You get what I mean? So if the D, let's say, is 4 angstrom, you do the measurement and you say that distance between A and B is 1 angstrom, you can say there is no bonding. Because all the experimental bonding is about in the order of less than 3 angstrom. If you observe a distance of 4 angstrom, you can forget, you can say, you can confirm there is no chemical bonding between A and B. So if you have the D equal to 2 angstrom, for example, you can say between A and B, there is one bonding. So let's say if the distance between the sodium and fluoride is 2 angstrom, it's very difficult to imagine another bonding between the calcium and oxygen 4 times of 2 angstrom, that means 8 angstrom, because at the distance of 4 angstrom, we will not consider the bonding already. You get what I mean? Yes? Oh, do you understand?
Yes. Yep.
Okay, thank you. This is something quite advanced. Normally, I keep later for the second year student, but because you raised very important question, so I take this opportunity to explain what we can basically understand from this bonding measurement distance. Okay. So here, experimentally, what you can see. So you take sodium fluoride, the bonding, the lactic energy is 910 kilojoule per mole. For cesium iodide, it's 600. So cesium iodide smaller than sodium fluoride. And you see calcium oxide is 3,400. It's almost 4 times compared with sodium fluoride. Okay, so that's smaller than calcium oxide. Sorry. Okay, so this experimental value, people can do the measurement. Yeah, may I propose that we have about 5 minutes break? because I need to make I would like to make a break, and then we'll be back later to finalize our lecture today. Okay, 5 minutes. Okay.
Okay. Yeah.
Thank you. Our lecture.
Yep.
Yeah.
Okay. So now we take a look how we can do calculation of the lactic energy. So by the definition, you understand very well. The lactic energy is the energy you need to put inside to break 1 mole of crystal to become gas ion, and anion. So it means the lactic energy is the energy you need to put here to break 1 mole sodium chloride solid to make sodium cation gas and chloride anion gas. So how we can calculate this? Then we based on the law of energy conservation. So in one closed cycle, because the law of energy conversion say that the energy will not be produced or not be consumed, but it can convert only from this form to another form. So it's also say in the closed system, the total energy of this system of a closed cycle will be equal to 0. Okay, so we say that if it takes sodium chloride solid, you can separate to sodium solid here and chloride gas here. So you have the energy formation of sodium chloride solid. And then you can put the energy to evaporate, we can say, sodium solid to the sodium gas. Of the chloride gas here. So now you go to the sodium gas and chloride gas. Okay, so from sodium gas here, which is neutral atom, you need to remove 1 electron. So you have ionization energy of sodium. So you have sodium cation gas plus 1 electron. And then this electron transfer to the chloride. So you make the sodium anion gas, and this represent by the electron negativity energy. So in total, you go from sodium solid crystal, you go in through 1 cycle, you go here to make it. So it say you will have minus delta S0F sodium chloride solid plus delta S0 of sodium gas plus delta F0 of chloride gas plus I1 of sodium plus ECl, okay, and minus delta S lactic will equal to 0. Okay, so if you start from here, from this point, sodium chloride, you go on 1 cycle back to this one, the delta E should equal to 0 because you come back to the same energy level. So that means you have this equation. So it say you can calculate the lattice energy when you know all other elements. Is this clear to understand?
Clear. Yep.
Okay. Good. Thank you. So now we move to the covalent bond. So when we apply the Octet rules to the covalent bond, we said that atoms tend to share electron until they are surrounded by 8 valence electrons. There are some exception. The Octet rule, for example, the hydrogen, here you have 2 electrons. They already make a covalent bond. But normally, to obey the Octet rules, for example, you have chlorides with a 7 electron and another chlorides with 7 electron. So the way the 2 chlorides obey the rule of 8 electron is that it takes 1 electron here or 1 electron here to share. So in total, after sharing, so in total, 8 chlorides here, we have 1, 2, 3, 4 pair of electrons, so 8 electrons, and other chlorides also have 8 electrons. Okay, so you can see that by sharing this single electron, the 2 chlorides can obey the rules of Octet rule. That means the rule of 8 electrons for the bonding. So by sharing the electron, they make the bond, the covalent bond. So when we look at the covalent bond, a slightly slow. Then we can understand that here you have nuclei, which is positive charge, and another nuclei with a positive charge. Okay, so 2 nuclei will have repulsion because they have the same positive charge. And you have electron with a negative charge. So between the electron, you have also repulsion. So that's why when you want to make to share 2 single electrons, you need to force the 2 single electrons to overcome the pairing electron energy. But at the same time, you have also attraction and interaction. On the where the repulsion and attraction is optimized. Okay, so at the end you can see that you have 1 nuclei here and 1 nuclei here, and in between the 2 nuclei here in between you have high electron density, but here and here you have low electron density. So you can say that in the covalent bond, the electron density will be localized in between the 2 nuclei, with the highest probability to find electron in between the 2 nuclei. Okay. Okay.
Professor, we can't see the screen anymore.
So here you have different type of covalent bonding. So for the first lines, you have single bond. So that means later you have bond order equal to 1. The bond order when we describe when we study the molecular orbital. For the moment, we stick with the idea that you have a single bond like this one. Carbon is hydrogen. You have a double bond, for example, carbon oxygen here. Okay, and we will have a triple bond, like nitrogen here. So my question is, in your imagination or your understanding, is it possible to have bond order not an integer number, but bond order of 0.5 or 1.5? Is this clear, my question?
Yes.
Yes.
What do you think? So what do you think? Do you think that we may have the scenario where you have a bond order equal to 0.5 and another like you have the bond order equal to 1.5, not 1, not 2?
I
I
guess
think no.
I think
No?
it's
No,
I think no.
no,
no,
Yes.
no.
because
And-
electrons should be going in pair in subshells.
So anyone think that yes, we do have?
Yes, I think we do have.
For example?
Like
It could be possible
it could be possible.
because
When?
anything is possible.
Oh, actually, yes, it could be possible in ionic compounds. No, sorry. In compounds such as like CO3,
CO3.
right? Maybe.
Anyone can give anyone who say yes can give me one example of the compound that you can expect the bond order 0.5 or 1.5. Just say 0.5.
Well, I remember that's just like the compound like H2 plus. It's like the compound of hydrogens, but they use some kind of energy. They remove only one electrons in the bound from between two hydrogens atom. So I think it bound order will be like 0.5. I think so.
Okay, so thank you, Wu. Yes, exact. Imagine that you have here, it's okay. So as you see that hydrogen have only one electron. So the second hydrogen have a second electron. So it's make bonding by sharing electron like this. Okay. So you will have one electron and one electron from other hydrogen. And now, as Wu mentioned, imagine that you have a way to remove this electron out. So you will have A2 plus represented by this one. You can say like this. Sorry. You can say like this. You still have one electron. So in this case, the bond order is, we can imagine, is 0.5. Is larger than 0 and smaller than 1.01. Okay. Wu? Wu?
Yes.
Yeah. So if we compare the strength and the length of the bond between the A2 and A2 plus, which one will have longer bond and weaker bond?
I think H2 plus will have a longer bond and also weaker.
Okay, yeah, that's it. So basically, when you have the bond order increase from the single bond, double bond, and to triple bond, then the bond gets shorter, and the stabilities of the bonding energy increase. Shorter bond means it's become stronger, more stable. Okay, so we can also, by accepting this idea, it means if you have a molecule of hydrogen, it's a single bond. It's not just stable, but stable. Now, if you want to cut it, if you want to destabilize, if you want to make it unstable, you have to find a way to remove one electron, then become H2 plus, which become less stable. Okay? In other words, when you have bonding, like carbon oxygen like this one, if you want to make it less stable, you want to break it, you can find a way to make it longer. You keep the same carbon, but you make it longer, then you can make it less stable. Okay? How you can make it longer? You can heat up, so the oxygen at the higher temperature, the oxygen will vibrate like this. So in one moment, because of vibration, you can see that the oxygen become here. So the bond will be longer. You get what I mean? So when you learn about the concept of the bonding, you can start to think how you can break a chemical bond. If you want to break a chemical bond, the first thing you can do is that you change the bond order. You change the bond order by decreasing the bond order by remove electron. When you remove one electron, the bond order will reduce half. So then bond order reduce, that means the bond length will gets longer and the bond become weaker, so you can have a possibility to cut it. You cannot remove electron, is that you make the bond gets instantly at one moment longer by making the vibration happen more importantly. That means normally all the bond chemical bond is in the vibration. You will not have a bond stand without vibrating. So you can make it vibrate faster. So when it vibrates faster, at one moment the bond length will increase, and the bond length increase, that means the bond become weaker, so you can cut it. Okay, so that's why later when you do the chemical reaction, most of the time it will increase, it will apply the temperature, it will heat up. When you heat up, you make the vibration stronger, you increase the probability to have a collision of the different molecule, so you accelerate the chemical reaction. Okay?
Professor, I have a question.
Yep, please.
So in some textbook, I read that CO3, instead of sharing two pair of electron, like in CO2, it share like one pair of electron and 1/3 of a pair of electron. Then what would be the bond order of that kind of molecule?
Okay, so CO3, right?
Yes.
Okay, this CO3 will be treated when we look at the resonance structure later. Okay, in the second part of the lecture. In next, we will discuss on that. Actually, CO3 we will have a scenario when the double bond will change all the time between the three oxygen. You get what I mean? I can go very quickly.
Yes.
It's very nice. Oof. Sorry. Um, okay, so I removed this slide already. So okay, we can imagine for similarly we will treat this case later when we learn the slide doesn't move. Yeah. For example, come on. Okay, like it's quite similar. Like we will talk about later, but can you see here the case applied to NO3 minus in this line, right? Can you see my slide?
Yes, we can see
Yep.
your
So
slide.
you see that? Yeah. So you see that you will have a double bond here, and if you put this double bond look like in the oxygen A and B and C, you will see that oxygen A difference compared with different. You can imagine that A difference B and C, right? But actually, experimentally, in the molecule of NO3 minus, as well as in the molecule of CO2 3 minus, 2 minus, you cannot distinguish the oxygen A, B, and C. The three oxygen are exactly identical. Okay? So we have a concept later, we call the resonance structure. That means the oxygen can move here, oxygen can move here. So you have this structure. And the oxygen can move, the double bond can move here, and then you have this structure. Okay, so basically the three structure will be identical. Okay, so now if you talk about the bond order, then here you have bond order equal to 2, here the bond order equal to 1, here bond order equal to 1. Okay, so it means, and because of this resonance structure, we will not say that the bond order of nitrogen oxygen here equal to 2 plus 1 plus 1 plus 1 equal to 4, and then you divide by 3, it's 1.3 something. No, we don't say that. Because of this resonance structure, we say that the NO here stand between the single bond and the double bond. So we can say the bond order here is 1.5. You get what I mean?
Yes, thank you, Professor.
But we will have this discussion on the resonance structure later, okay? Because as I explained in my lecture in previous section, that remember you guys, important. You need to take care of this message. Take the message important. The chemical bonding theories we are learning is our current understanding to explain the experiment that we observe when we do experiment with the chemical compound. The chemical bonding theories we are learning, we are discussing, is our current understanding. That means before the understanding will be different, and could be in the future with your contribution, the understanding about the chemical bond can change. And later we will tell you, we will have an exception that now when we talk that the carbon have a maximum 4 covalent bond, it will no longer correct. You have some case the carbon have a more than 4 covalent bonds. So we say that the understanding of the chemical bonding is evaluate and progress on the time. So now we are talking about our current understanding. So for example, when we use the language structure to draw in NO3 are not identical. It means that I mentioned the oxygen A and B and C, A will be different, B, C. It doesn't matter if we say that they are different. But now the question is that if they are different, then we expect that they behave differently in the chemical reaction. That means now if you put the compound X inside to react with NO3 minus, you expect that X will react on the A, but not on the B and C. But when we do the chemical experiment, we cannot distinguish A, B, and C. The three oxygens are exactly identical. So that means our bonding theory that we are explaining is not really correct, because our bonding theory say that they are not identical, but experimentally we see that they are identical. So we need to propose a new thing we call the resonance structure. That means actually the three ones are identical because the double bond moves all the time between the three oxygens. So that is our proposition. Whether we can see the double bond move or not experimentally is other thing. You get what I mean?
Yeah.
Okay. But you know, because the most serious thing for me is that maybe you take the chemical bonding theory like an absolute thing, and if you see something you cannot explain by the bonding theory, you say that it's not correct. So I would say that the correct thing is experimentation, and our explanation can be our understanding can explain the experimentation or not. It's depending on our current understanding, and it can change all the time. Okay, so now we know about the type of bonding. So we say that the bond strength, when you go from the single bond, a double bond, a triple bond, the bond strength increase and the bond length decrease. So when you have a single bond, it's longer than double bond and it's longer than the triple bond. Now we move to the last important thing before we stop, the bonding polarity. So we have ionic bonding and we have covalent bonding. The bonding polarity is measurement of the equality of the shared electron. Okay, so that means here is following. You take one electron from this hydrogen and another electron from this hydrogen. They share the two electrons to make the molecule, to make the chemical bond, the covalent bond. Now the question is that you have a two electrons supposed to be equally shared between the hydrogen and hydrogen, the two atoms. Does that mean this atom can say that, okay, we can consider the two electrons as mine. Okay, so we say the electron density localized on this hydrogen and the electron density localized on this hydrogen will be equal. But you have also a scenario, for example, when you have hydrogen and the fluorides. So hydrogen have only one electron and the fluorides have 7 electrons. Now you make the bonding, you have hydrogen and the fluor like this. Okay, then this shared electron is more localized in the fluor than the localized in the hydrogen. Does that mean you have a higher density close to the fluorides than the electron density localized in the hydrogen? How I can demonstrate this one? A very funny one. Before we go to the equation and so on, I talk about the concept. Let's say the two students in this class start to say that, okay, chemistry, general chemistry is boring, biology is also boring. Now we want to make money. Okay, so we want to set up a new startup, a company. So to start a company, you need to have budget, you need to have funding. So the two guys will say that, okay, we pay the same amount of money, and then we become co-owner of our company. So if X of you contributes the same amount of money, then the company becomes co-owner by two of you, and two of you will have a similar responsibility, the same capability to make a decision. Okay. That is in the case of perfect covalent bonding. So both of you have the same capability to decide, make all the important decisions for your future of company. The second scenario, so in that case, we say that the between two of you, there's no difference. So the bonding between you two is equivalent. So you have a non-polar bonding like this. Now there's second scenario. One of you have a new technology, like you create a new software, but you don't have money. Another friend is very rich. He has money, but he has no technology. Now, if the guys having technology want to set up a new business, he will have a difficulty because only technology can have a difficulty to reach the market and so on. The guys with the funding but without the commercial transfer and so on, whatever, but not in the field of technology. Now, two guys decide, okay, I contribute my technology, you contribute your funding, and then we build a new technology company. But you see that this company, the contribution of the two guys are not identical. The guy contribute technology have very low capability to manage funding. So he will be not the guy who develop the markets, who take care of the advancement, who take care of the selling of process and so on. The guy who invest money probably have no understanding or very limited understanding about the software, about the product. So he will be not able to be in charge of technological development of this product for the next generation of product, but he will be very good at using of money, take care of marketing and so on. So you see that in this company, of course, both will be the co-owner of this company, but the responsibility will be not the same. So the electron here, money, the benefit of the company will be more localized in the guy who make the contribution of funding than localized in the guy who make contribution of technology. Even they are sharing money and technology. So saying that this is a covalent bonding, but polar. You have polar covalent bonding because of the funding. If we consider electron as the funding, then the funding will be more localized in the pockets of the guy who contribute money than the guy who contribute technology. So my explanation is clear for you guys to understand the concept of the covalent bonding.
Yep.
So we talk about the bonding polarity. Okay. So if you have a pure covalent bond, like the guy who both put money, who both put the equal contribution in the technology to start up, then the pure covalent bond, the neutral atom held together by equal share electron. That means 50% of electron, you get 50% of probability you will find electron in the atom X, and 50 other percent of probability you will find in the atom Y. So that means the electron density you will find in the two atoms X and Y will be equal, or M and X will be equal. You will have the case of polar covalent bond. when the charge will be held together unequally. That means one guy like X here will have more chance to have electrons. That means it will have a higher electron density localized near to the nuclei of the X than the electron nuclei localized in the nuclei of M. And if you have ionic bond, so that means you have an opposite charge ion held together by electrostatic attraction. So that means you can say 100% of time you will find electron in the X at the anion. Now the question is, how could we tell if a given bond is polar covalent bond or non-polar covalent bond? Let's say if I give you one chemical bond MX, how can you justify? How can we predict whether this bonding is polar or non-polar? So time is up. I propose that we stop here. I will upload on this slide for in the Moodle. So next week we will not have class. We will continue later, and next week we will take time to have a midterm exam. Is it okay?
Okay.
Okay. So I received one question from one of you guys saying that next week it will go for the military training. In that case, you guys, you send email to me to make sure that all of you who go to the military training will not have midterm, and then I will collect the list of all of you who will be absent in the next midterm, and then we can organize another midterm. Okay, but make sure that you are absent solely because you participate in the military training. Other reason will be not accepted. Okay. You get what I mean?
Okay.
Okay. So thank you guys. Good luck for the preparation for the midterm next week. Bye bye.
Bye bye, Professor.
Thank
Goodbye.
you for lecture and bye bye.